So here's a problem that I would like for you to try. I'm going to read it out loud and just talk about it for a minute. You have 24 Airheads and 18 fun-sized bags of Sour Patch Kids. You want to use all of them to make treat bags for your little sister's birthday party. If all bags must contain the same items, what is the greatest number of treat bags you can make? What will be in each bag? Solve and draw a diagram to prove your solution. So let's think about this for a minute. Make sure we understand what it's saying. We want to make treat bags like you might get at a birthday party or something like that. And normally when you go there, the bags pretty much all have the same thing in them because otherwise somebody's going to fight about it. So for example, if there were three Sour Patches in a bag, then all the bags should have 3 Sour Patches. If there were 9 Airheads in a bag, then all of the bags should have 9 Airheads. So the question is, if we want all of our bags to be the same and we want to use all of our Airheads and all of our Sour Patch and have nothing left over, then what is the greatest number of treat bags you can make? So if we think about that for a minute, could we put 1 Airhead in each bag and make 24 bags? Well, sure, that would work for the Airheads, but then we don't have enough Sour Patch Kids to put 1 in every bag, so that's going to leave some people not happy, so that can't be it. Maybe we say, well, what about 12? Let's make 12 bags. Well, that works for the Airheads because if I have 24 Airheads and I want to make 12 bags, then I can put 2 Airheads in each of the 12 bags and everybody's happy. They have the same number of Airheads. But wait, that won't work because with 18 bags of Sour Patch, we can't put those evenly in 12 bags with nothing left over. So that's not going to work either. So I might start thinking about, well, what would work for this? And I might start with the 24 and say, well, I could do 1 in each bag and have 24 bags. Or I could do 2 in each bag and have 12 bags. I could do 3 in each bag and have 8 bags. I could do 4 in each bag and have 6 bags. And thinking about it going the other way, I could do 6 in each bag and have 4 bags, 8 in each bag and have 3 bags, 12 in each bag and have 2 bags, or 24 in each bag and have 1 bag. So those are my options for how I could split up my Airheads and have nothing left over and have the same thing in every bag. And it might be helpful to think about, well, what about for the Sour Patch? Well, for the Sour Patch, I could do 1 bag with 18 in each bag, or 2 bags with 9 in each bag, or 3 bags with 6 in each bag. Or I could do 6 bags with 3 in each bag, 9 bags with 2 in each bag, or 18 bags with 1 in each bag. If I look at this really carefully, I'm going to notice that the greatest number of bags I can do is 6 bags. I can do 6 bags because that's the biggest number that goes into both 24 and 18. Well, if I think about that, if I'm going to do 6 bags, then each bag is going to have 24 divided by 6 is 4. It's going to have 4 Airheads. And it's going to have 18 divided by 6 is 3. It's going to have 3 Sour Patch. So I'm thinking that I'm going to be able to make 6 bags, and each bag is going to have 4 Airheads and 3 Sour Patch. And if I wanted to look at a picture of this, this is what it could look like. So notice I've got 6 bags, and each bag has 3 things of Sour Patch, 3 little bags of Sour Patch, and each bag has 4 Airheads in it. So that solution will work. I have used all of my Sour Patch and I've used all of my Airheads with nothing left over, and every bag has the same thing. So that solution will work. I have 4 Airheads and 3 Sour Patch in each bag. Now let's think about what this actually was that you were doing. What you were really working with here were factors. And you were looking at 2 different numbers, 24 and 18, and kind of comparing their lists of factors. Well, when you do that, what you're actually doing is called finding common factors. And in this case, we were looking for the greatest common factor, the biggest number that 18 and 24 had in common. So we usually abbreviate this GCF. GCF stands for the greatest common factor, and it means the greatest factor that 2 or more numbers have in common. And there's 2 ways we generally do this. One way is we use a listing method, and that means we list the factors of each number, and then we compare our lists. So For 12, if I were going to want to find the greatest common factor of 12 and 20, I could say my factors of 12 are 1 and 12. Remember how we talked about finding factors. We don't want to just write a list in order. We want to think about the factor pairs. So 1 times 12, 2 times 6, and 3 times 4. Those are all my factors of 12. My factors of 20 would be 1 and 20, so 1 times 20, 2 and 10, 4 and 5. Now I start looking for common factors. So that means numbers that are on both lists. 1 is on both lists because it goes into both 12 and 20. 2 is on both lists because it goes into both 12 and 20. 4 is on both lists. It goes into both 12 and 20. Those are all of the numbers that are on both lists. So my common factors of 12 and 20 are 1, 2, and 4. That means my greatest common factor, the biggest number that they both have in common, is 4. Now, you've probably seen this listing method of finding greatest common factor before, and it's a great method. It's very reliable. It works. The issue sometimes becomes if we leave factors out accidentally, then it can be really hard to compare the list of factors. So we're going to look at a second method you could use as well, and it's really related to upside down division, which we've used to do prime factorization. So if we look at this, you can call it the list method or the tic-tac-toe method rather, or the ladder method. It kind of looks like either of those. You can also relate it to upside down division. It's like the upside down division because it's like upside down division in that we're going to look for a factor of two numbers, not just one number. We're not going to divide just one number. We're going to divide both numbers by the same factor. Now, when we do it with prime factorization, you have to use prime numbers. You don't necessarily have to do that with greatest common factor, but you could. You could start, for example, by dividing both 24 and 60 by 2. And then we're going to divide 24 divided by 2. That's what's going to go in this next column or underneath the 24. And 60 divided by 2. So 24 divided by 2 is 12. 60 divided by 2 is 30. So now I'm done with that row. Now I want to look at 12 and 20 and find any common factor of 12 and 20. I might again say, well, they can both be divided by 2. So 12 divided by 2 is 6, and 30 divided by 2 is 15. Now I'm going to look again for any common factor of 6 and 15, and I have 3 as a common factor of 6 and 15. 6 divided by 3 is 2, and 15 divided by 3 is 5. So now I get to the point where I'm looking at 2 and 5, and 2 and 5 have no common factor. They have only one common factor. The only common factor they have is 1. I could put that there if I want to, and that's how I know when I'm done. Now let's look and see how we find the greatest common factor. We're going to find the greatest common factor. We see a note over here that says multiply the numbers in the left column to get the greatest common factor. So that means I can multiply 2 times 2 times 3, and I don't necessarily need to do the times 1 because multiplying anything by 1 just gives the number. That's what the identity property tells us. So 2 times 2 is 4, times 3 is 12. The greatest common factor of 24 and 60 is 12. Now you might be thinking, I get it, I'm with you. However, I would not have started by dividing 24 and 60 both by 2. I might have started with something else. So maybe you would have started with 6. And that's okay. 24 divided by 6 is 4. 60 divided by 6 is 10. 4 and 10 can both be divided by 2. 4 divided by 2 is 2. 10 divided by 2 is 5. The only common factor that 2 and 5 have is 1. So I'm done there. And my greatest common factor is 6 times 2, which is 12. So notice I get the same answer. I even get the same answer. Let's say maybe I say, well, I'm going to divide them both by 4. 4 goes into 24 6 times. 4 goes into 60 15 times. 6 and 15 can both be divided by 3. 3 goes into 6 twice. 3 goes into 15 5 times. The only thing left that goes into both 2 and 5 is 1. So I'm done. And my greatest common factor is 4 times 3, which is 12. So notice no matter what I start with, as long as I'm using common factors, I'm going to end up with the same greatest common factor. I want you to try with 90 and 72. Let's try that one together, and then I'm going to give you a couple to try on your own. So 90 and 72. It's pretty big numbers, but you might hopefully pretty quickly say, ooh, I know that they have 9 in common. 9 goes into 90 10 times and into 72 8 times. All of a sudden, this is a much easier problem because 2 goes into 10 5 times and 2 goes into 8 4 times. My only common factor is 1. And now my greatest common factor is 18. 9 times 2, which is 18. So the greatest common factor of 90 and 72 is 18. That means the biggest number that goes into both 90 and 72 is 18. All right, so let's think about 24 and 35. Try that one, see what your thoughts are. Pause it while you're trying, and then when you're done, hit play and see if you've gotten it correct. So this is the tiniest bit tricky, but we have to think about this kind of stuff. Notice the only thing that goes into both 24 and 35 is 1. They have no other common factor other than 1. Therefore, their greatest common factor is, in fact, 1. All right, try 96 and 64. Pause it while you're trying it and then see if you've done it correctly. Now this one might have taken some work, but if you did it all correctly and your computations are all correct, then you should have ended up with a greatest common factor of 32. If that's not what you got, go back and look. Somewhere in your work you have made a mistake in your computations. So go back and see if you can figure out where you went wrong. Now I want to go back to our original problem. Our original problem, we now hopefully realize really is really asking for the greatest common factor of 24 and 18. So I could absolutely use this listing method, which is essentially what I've shown here with writing the multiplication tables. However, if I do it with our upside down division, or we call it ladder or tic-tac-toe, if I do it with that method, I want you to notice something. So I might divide those both by 2 and get 12 and 9. Divide those both by 3, and that's going to give me 4 and 3. So now I'm done. And my greatest common factor is 2 times 3 because of this right here. And that's 6. So that's going to be our 6 bags. But what's kind of interesting about using this method, let's go back and take a look. There were 24 Airheads and 18 Sour Patch. Notice I end up with 4 Airheads in each bag and 3 Sour Patch in each bag. So if you do use this method for finding greatest common factor when you're solving a word problem, notice that you can get more than just your greatest common factor there. There's more information there that it will give you. So you might find that to be helpful in solving word problems. All right, I have one more thing for you. If you want just a little more practice with greatest common factor, I have sort of a challenge practice for you. I want you to take a look and see if you can figure out which missing numbers you need to fill in those blanks. Pause while you do it, and then you can check once you've finished. So hopefully, if you've done this correctly, these are the answers you've gotten. Whoops, actually my last one should not be 60. It should be 45. But these are the answers that you should have gotten. Notice you could have gotten some different answers for the GCF of being 1. You could have also gotten 25 and 8 or 25 and 48. Those would have also had an answer where the GCF was 1. So there was more than one way you could have solved that one. Everything else, however, I believe you had to have the answer that was given.